Hello, we are Group 20. Our article was on the Internet of Things, Smart Cities. Our group consists of Batt, Graham Briggs, and Ricky Myers. I'm Ricky. So, to introduce our topic, the Internet of Things is the general name given to a sizable amount of devices connected via some network protocol, electing flexible and extensible interface and control of many real-world systems with or without human interaction. This is generally, we have these throughout our houses now. You'll recognize them as your home nests, controlling your thermostats remotely, or even your Ring doorbells, being able to see who's at your door via your Wi-Fi network. The implementation of the Internet of Things is currently hindered by a lack of standardization, and there are difficulties in marketing the approach, which leads to fewer investments. Now, the problem with having all of these different Internet of Things ideas is that all of them are made by different companies, which means that they have different practices in their software development and their implementations, which means that anytime we want to encapsulate all of these in a single home, you have to have some overarching network. Now, this article deals with trying to take this idea of the smart home and extend it further into an entire city. So they want to take the same paradigm and enforce it on an entire city. And they decided what better way to try this than to actually implement it somewhere in a city as a test run. So they decided Italy, Padova to be exact. So in trying to realize this goal, there are a couple barriers that they realized are prevalent. The most foremost is the political barrier. There are many different ways that you could use actuator sensors throughout the city to detect things, but which ones do you do and who gets to choose? There are stakeholders in many of these realms, and there are people that are recipients of the benefits of these, but they come at costs in who has to pay and who gets to decide on that. There are the technical barriers. Many of these devices are using different protocols. They must be integrated in different ways, and that doesn't even include the transfer of the data, the power going to these devices, paying for the devices themselves, which brings us into our next point, the financial aspect. There's currently not very clear marketability to the governments themselves on why they should implement this. Many cities are short on cash as it is, and trying to get everything online is an expensive thing without a very significant payoff. You could argue that this would be through lower administrative costs, but still it is a large cost to bear. There's also the ethics and security, which we'll get into in a second. So some of the potential improvements that they were mentioning were building health. There are many older buildings in this region of Italy, and if they use sensors to monitor it through stress vibrations, then they might be able to avoid having to send people out to determine whether or not the buildings need to be repaired. They referenced waste management, which if they had special devices on the waste bins, they'd be able to route better and determine who needs to pick the garbage up and optimize the routes, but this would require expensive waste baskets. Air quality control, they would be able to track pollution, report on greenhouse emissions, and try to track their how well they're doing with climate agreements. Noise monitoring, they have multiple purposes, but several of them are controversial because if you have noise monitoring, it means you probably have listening devices, and then the question on whether or not the government is recording and listening to those comes into play. Traffic, you might, if you have sensors telling you where people are on the road, you might be able to determine optimal routes or reroute traffic to mitigate traffic jams. Total city energy management, once again, there are directives to reduce total energy use, so it could be used to that end. Smart parking, which could be used to help people find parking, know where parking is available, and once again, that would help mitigate traffic and make people happier. And finally, smart lighting, which could reduce energy by only turning on when people are around and need it. Next, we will go to Graham.
Hello, I'm Graham Briggs, and I'm going to be discussing the network architecture and devices of a smart city like the Padova experiment. So the Padova experiment used a centralized architecture, that is, the users and the periphery devices interact with a central server, where that central server stores the data gathered by the Internet of Things sensors and interact with it through a website. So on the periphery, there are constrained communication nodes. These are really small, low cost, and low resource devices. The target was about $10 or less. And to achieve such low prices for these devices, they necessarily had a kind of a slow data transfer. Often they were in a lossy environment. And so they used some network architectures like CoAP and UDP, and I'll get into those in a second. These devices are anything like a temperature sensor, a humidity sensor, sometimes valve actuators. They interact with the environment. That's their goal. And the idea is you have a lot of them because they're so cheap and so small. You can distribute them across the entire city and be able to like heterogeneously interact with and measure what's going on in your city. So the on the other side you have the servers and the users, and those are more traditional legacy internet unconstrained communication protocols like HTTP and TCP. If we go to slide 6, we'll see a little bit about the constrained device communication. So the unconstrained devices, unconstrained protocol, like the server, like the clients and everything like that, and the users, are pretty verbose in their data transfer. A lot of times, these types of devices will communicate via XML, which is a both machine and human readable data transfer document type, if you will. But it has a lot of overhead and headers and such. Like, for example, there's a version ID that you have to send at the beginning that contains a lot of data, and when you're trying to send, a couple of kilobytes an hour, you don't have a lot of ability to handle that overhead. So these constrained devices used EXI. It stands for Efficient XML Interchange, and it really shortens and compresses XML. Before I was talking about that header that has a version ID, and names and everything in XML. That's shortened to 2 characters in EXI, for example. So it's a much smaller data size that you have to send. The application layer uses a RESTful protocol like HTTP called CoAP, but it's a lot, of course, more lightweight, and sends a binary encoding of all the data in UDP packets instead of TCP. So you don't need to establish a client server connection. The Internet of Things devices can just send their packets over and over until they get some confirmation that at least one of them was sent, and then stop. It makes them a lot cheaper. And similarly, the network layer is along the same vein, a lot smaller and cheaper. It uses in the Padova experiment specifically, they used IPv6 low power wireless personal access network. IPv4 is now out of addresses, so IPv6 has more, and their paradigm can be used with the IEEE 802.15.4 link layer. It's another low power wireless personal access network standard. So like I said, the main devices needed for this concept are the backend servers. So they're kind of like the backbone, right? They contain the process and they allow access to the data gathered by the Internet of Things nodes. These can be, cloud servers. In fact, that's their definition, kind of. Then also you need gateways. So you need a way to connect your servers to your Internet of Things devices. And these gateways also have to translate between the constrained and unconstrained communication protocols. Now, you don't need one gateway to translate all of your traffic, right? You can have one gateway to translate between HTTP and CoAP. You can have, your innermost gateway translate between your low power IPv6 to a more traditional IPv6, for example. But at the end of the day, it's got to get the data from your constrained devices to the unconstrained server. And then the third core category of devices are your Internet of Things periphery nodes. These are, again, those small, low-cost devices spread throughout the city that gather data or interact with the environment and control the city. And so here's an example of some of the requirements that the Padova team came up with for their smart city. I won't go over all of them because that would be too long, but if we look, for example, at the structural health monitoring. So they had some seismograph type integration in buildings to look at their structural integrity. You can see that they communicated over that 802.15.4 low power wireless network over Wi-Fi and Ethernet. Their traffic rate was required to be one packet every 10 minutes, so they're pretty slow, and they could deliver. They could tolerate a 30-minute delay for regular data, but only a 10-second delay for an alarm. So an alarm would be if something was going wrong, of course, in your building. And you can see here they're battery powered, so that's right. That lends credence to why they need to be really small and low cost. They not only don't have the ability to translate at high data rates, but they need to save power and not have their battery changed or charged. So with that, I'll hand it off to Kay for an overview of the Padova project in general.
Hi, my name is Batt. I'm the third member of this group. I'll be concluding the remainder of this presentation on IoT smart cities. The practical proof of concept of this study included the Padova experiment. This was a practical implementation of the IoT paradigm where the details of the technology were outlined earlier in this presentation. It was taken place in a small city in northern Italy, just west of Venice, where the University of Padova, in conjunction with private investors and the city municipality, essentially implemented this project. It is the practical application of an urban IoT. This project consists of approximately 300 nodes. The sensor network testbed was realized to a real-world application where the city street lamps were equipped with various sensors for collecting environmental data. These sensors included light intensity, temperature, humidity, and benzene. Many interesting learnings were acquired from the data collected from this working system. One example include the regular environmental patterns that were observed from the various sensors that picked up many information from the streetlights. One example included the realization of a midday rainstorm that resulted in a drop in light intensity and an increase in humidity, as well as an increase in benzene. Potential to expand on this proof of concept include the opportunity to develop a next generation combining sensor system to paint a better full picture of the real world. Padova streetlight sensors were passive data collection only for the sake of simplicities of this implementation. The next steps could include a dynamic system that would both have actuators and a feedback control. Though this is a relatively simple setup, it still encompassed various technologies, including the link layer technology that Graham had just explained. Early success example of a simple setup, this provides the path forward to explain and build an idea on smart cities. In conclusion, this practical application used small, low-cost data-constrained nodes. It also used the centralized architecture that we already discussed. This proof of concept establishes confidence and a base platform to market the potential to grow in the area of smart cities. A simple example is both easier for both public citizens, private investors, and city municipalities to trust a real proof of concept. Data-driven examples have more weight than an abstract idea. Overall, in this paper, we learned about the current IoT systems available today, their limitations, ethics, cost, and areas for potential improvement. The author's goal in this study was the practical proof of concept was to help clear the uncertainty that still hinders a mass and seamless adaptation of the IoT paradigm. Overall, there are many works that are being done in the Internet of Things application, and smart cities is being one of them. And I hope that you are able to at least get some appreciation for the potential public benefits that this system can provide for everyone. Last slide includes just a brief link to our additional sources. Thank you for listening. Goodbye.